Welcome to Machine Learning with Python workshop. My name is Yuko, Assistant Adjunct Professor of Mathematics and Biostatistics, and serving as Collaborative Fellow for QC Bio Collaboratory. So this is one of the workshops in the Collaborative Workshop series, and if you are taking this workshop as part of, what was the class number? Bioinfo 275 A, B, or Research 199 or 99, the attendance is required, and the grading is based on your homework and quiz. So that will be there as always. Yeah, so I am currently working for mathematics department and biostatistics department, and before moving on to that position, I was a postdoc in Department of Biostatistics with Dr. Poiseau, and Department of Computational Medicine working with Dr. Ken Lang. And my research area is over computational statistics and high performance computing for big data analytics, including biobank scale data. I developed genome-wide association studies methods for longitudinal data and developed methods for population structure inference, such as using adversarial models using GPUs. But the topic for this workshop is Intro to Machine Learning using Python. By the way, let me ask you a couple of questions. What interested you to register for this workshop? Could anybody tell me? Anybody? Yep. Because it is important for your data analysis in your lab. Great. Anybody else? I know some of you are just taking this to get academic credits from Bioinfo 275, of course. Other than that, anybody else? Yep. Huh? Sorry? Just for fun. Oh, yeah, there's a great reason, actually. Yeah, academically, machine learning has been a very hot field in pretty much any area these days. And this workshop is for giving basics for those machine learning and AI applications. Let's get started this. Let's start with this. What is machine learning? It had recent surgeons in recent decade or 1.5 decade, but the concept of machine learning originates from 1950s, actually. Arthur Samuel was the person who coined the term machine learning back in 1959 as a field of study that gives computers the ability to learn without being explicitly programmed. So the paradigm applied here would be that the computer learns a model from the data. So learning is done by our computer. Then what do humans do? Human defines data that computer learns from. Human feed in the data for machine to learn the model and define algorithms, defining how the machine would learn. That algorithm would be procedures that is run on data to create a model, and that will include linear regression, decision tree, support vector machine, deep neural networks, etc. And also defined by human would be some hyperparameters. Those would be external configuration for each algorithm, such as how much should the computer try to simplify the model, or how much complex of a model you would want. So the goal of this workshop should be learning how to feed the data for computers, how to choose the algorithm, and hyperparameters. And the goal of this workshop would be providing basic information for you to do that independently and increase some knowledge with some online resources. So what is our goal here? For you to become independent and use online resources to your favor. So you have your idea about what to do with machine learning. And later on, after this workshop, you would be able to find out some online resources such as Google, Stack Overflow, cross-validated for statistical information, and some textbooks. This workshop is based on hands-on machine learning with Scikit-Learn and TensorFlow book. And some other classics are there in the field. Pattern recognition and machine learning by Bishop. And the deep learning textbook is also there by Ian Goodfellow and other fellows. And of course, these days, there's ChatGPT. So use of online resources became much, much easier than before. Here's an overview of the workshop content. Today, we start with fundamentals and motivation, overview of machine learning, short review of Python, introduction to the tool we will often use in machine learning, as well as data science in general, Jupyter Notebook and Jupyter Lab, and some common use packages as well, including NumPy for numeric array computation, matplotlib for visualization, and the main package we work on with is called Scikit-Learn. And for day 2, we will talk about classification and cross-validation. Important topics in machine learning would be the classes of problems, and those will include classification and regression. Day 2 is about classification, identifying which class does each of the sample belongs to. And we will talk about cross-validation. That is about how to choose your model. So we learn how to objectively assess the performance of your models and how to choose and use the models from the package Scikit-Learn. And one of those methods would be called k-fold cross-validation. Day 3, this Thursday, we will talk about some regression where the target is continuous values rather than discrete values in classification. And we will talk about some unsupervised learning cases. Classification and regression are supervised learning where our goal is to predict the target values, the class labels, or the regression values associated with the samples. But with unsupervised learning, the goal is to work with unlabeled data, working with about learning the underlying structures within the samples. Those will include clustering methods, grouping the sample points into several clusters, and PCA, principal component analysis, as well. And we will talk about some conclusions. Homework and quiz will be there. Homework will be simple data analysis tests given throughout days 2 and 3. And how that works will be described later. And for quiz, there will be around 10 multiple choice questions given at the end of the workshop. And those two are the key assessment items if you take this workshop to earn UCLA credits. Deadline 10 days after the conclusion of this workshop. Sorry? The last bit? The deadline? Oh, deadline will be 10 days after the conclusion of this workshop. So 2 Mondays from today, that will be. By the way, if this is first workshop you're taking for user credits, keep in mind that each workshop might have different structures for grading. The weight of each item that is maintained by Mr. Eloy Lopez. But different workshops may have different means for conducting homework and quiz. And if you have issue with any of the workshops, the best way is to talk to the instructor if that is directly related to specific workshop, and to Mr. Eloy Lopez if it is about comments general to the workshops, or is about other parts of grading not mentioned here. That includes participation, I think. That part, I have no control of it. That belongs to Mr. Eloy Lopez. Does it make sense? Let's move on to the tools to be used for this workshop. The first tool you will use, we will talk about, is Jupyter Notebook or Jupyter Lab. That is the application you are looking at on this web browser right now. This is a highly interactive way to work with computer programs, especially more high-level languages such as Python, Julia, or R. It is open source, and it lets you create and share documents containing code that are runnable in the format of Jupyter Notebook format, the extension being .ipynb. .ipynb, that is actually short for IPython Notebook. That is precursor to this Jupyter Notebook, but the extension is still kept. This is originating from the IPython interactive Python project back in the days, and they expanded their scope to other languages and got this fancy new name, Jupyter Notebook. And Jupyter is actually putting 3 programming languages together. The languages that I mentioned just earlier: Julia, Python, and R. And these notebooks can contain live code and hypertext using the markdown format in the text. And that lets you do something called literate programming. You can document what you're doing and show the result of the code in same places. Jupyter notebooks are not the only thing lets you do literate programming. In R Studio, there is a tool called R Notebook specific to R. And in MATLAB, there is a thing called MATLAB Live Script. But the main language we are using here would be Python. So we will use the tool closer to Python, which is Jupyter Notebook. And I use the term Jupyter Lab, and that is an extension to Jupyter Notebook for better user friendliness. And the interface you are seeing here is that of Jupyter Labs. So there are several advantages and disadvantages between using this kind of interactive interface and running code from your console. Running code from your console, that means running some code from here on your terminal and writing Python to get the interface to Python language. Doing things like this. And what would be the difference between these two? The advantages for using Jupyter Console, like just I showed, is that is considered the default way to run Python. And if you are running your job remotely, away from the computer that runs Python, for example, if you're working on a server, for example, if you are working on a node on, what was that called? Hoffman 2, then working with Python console would be the most straightforward way to get there, because that is rapidly available and it is almost always there. However, the limitation of it would be that it is hard to share the code with each other if you run Python code this way, and these cannot contain figures. So if you plot things, you need to find a way to get to the figure file or open a new window containing those figures. And it is not ergonomic. On the other hand, if you are using literate programming structure like Jupyter Notebook, the pros would be that these files are shareable and it can contain plots and figures you create. And that persists on those files, so you can share those plots included in these files. And the interface is more user-friendly. The limitation would be that it is a separate package from the core Python, so it needs to be installed. And because of that interactivity, it uses lots of resources and it may be slow. So it is not really suitable for large projects. So for short projects, short code for data analysis, or for this kind of workshop situation for teaching, Jupyter Notebook is great for these situations. By the way, as I mentioned, Jupyter has its target expanded to other languages, and you can install kernels for other languages different from Python, including Julia, R, MATLAB, even C++ these days. And nice thing is that Jupyter Notebook is included in the Anaconda distribution of Python. There is something to talk about that Anaconda distribution. There's not official release of Python in any way. It just includes official installation of Python along with other packages. Python is a bit old and it actually predates some of the nice concept of package managers. So third-party people built this kind of thing. And they are shipping Python with many packages suitable for scientific applications, including NumPy, SciPy, Matplotlib, or Scikit-Learn. So we are using a third-party distribution of Python in Anaconda, and that is massively popular thing to do in academic setting. Let's get started with the installation. Option 1 is opening Anaconda Navigator if you have installed Anaconda on your computer already. Do I have Anaconda Navigator open? Yes, I do. This is what it looks like in Anaconda Navigator. And this would be something you'd be seeing from Navigator if you just open up Anaconda Navigator. And from there, you will be able to see something saying Jupyter Lab. So you can launch Jupyter Lab from here. And from that Jupyter Lab, you can navigate to the location where the course materials are. I shared the link to the materials earlier today. And you can download and you can navigate to the folder where the materials are downloaded. And you can move into day 1 and open day 1 notebook.ipynb. Another option we provide is Binder. If installation on your local computer fails, we can actually run a notebook from a cloud service. The link is provided on the course website. why I sent this around earlier today, and on the link. You can see the materials here, and you can download the materials by clicking on code. And if you are familiar with GitHub and Git, you could try these commands. If you're not, you can just press this button to download every file in a zip file, compress in a zip file. And you can expand that file, and you will be able to find the .ipynb files. That is what I have opened here. And if that doesn't work out for you, I have put something here. There's a launch binder button. If you click on it, it will give you some small cloud environment that lets you run some Jupyter Notebook. And you'll be able to run some code from here. A slight issue here would be that those machines get turned off after several minutes. So you might need to restart it each time, but it will serve as an alternative to having Jupyter Notebook on your computer. When you open a notebook, you will see this notebook interface, and you can run code in the cells. Have you guys opened this interface? Anybody having trouble? Yeah, you can run each cell by pressing a play button up here or by pressing Shift Enter on the keyboard. And the default action of Jupyter Notebook is that if the last line of the cell assigns something, nothing is displayed. Here, 5 times 3 plus 2 is assigned to a variable x. Otherwise, the result of the last line is just displayed. So we could do something like this. Y equals 7 times x squared plus 0.6 times x. And we define z as 1 divided by x. Remember, if you do a division like this in Python, the result is always floating point, even if it is division between integers. And if we run this, we get y times z displayed right here, because that is because last line of the cell is a value, so it gets displayed. Another way to display information is using print function. Print y times z will show you 119.6 up there. We had a for loop in Python for values in range x, range 10, assigned as value x, that will be numbers going through 0 to 10, not including 10. So we get element 0 to element 9 printed out by this line of code. The variable element is replaced by each value in this collection. And finally, it is print x, printing the range here. What happens if we go back and run this cell again? What would we see? We would see a type error because x now is not a integer defined here. X now is a range. And these operations are not defined for a range. So what to keep in mind here is that the order of cell execution is important. Here, x is overwritten by this range and not maintaining the value here. Why? Because when you run Jupyter Notebook, there is actually Python console running at the back. Something like this is running behind these Jupyter Notebooks. So when you run a code cell, that code is executed within that kernel, and any output is returned back to the cell to be displayed. And that kernel state persists over time and between cells. And that means that there will be one kernel running for the document as a whole and not for individual cells. So after running this, x is range. So if you go back to the second cell, we get an error. So be careful whenever you go back and make sure to run all the relevant cells again. And actually, we can restart the kernel, the Python console we are running at the back end. There is a kernel button, and there's restart kernel. Pressing this will restart the Python kernel. Everything swept out. If I press this now, X will be gone. There also are nice things, restart and clear outputs, which will just remove the outputs you see here. Restart and run all, which will restart your kernel and run each of the code cells from the top to bottom. And there's interrupt. You can stop executing the cell currently running if your code is stuck in an infinite loop, or if it is somehow not finishing running. It is similar to pressing Ctrl+C in the console, and it is useful when the kernel hangs or trapped, or you are trapped. That is what stop button does. So if you do this kind of thing, this is a basic infinite loop, right? If I run this from console, it will be there forever. It will be just running past, doing nothing, but never moving outside of that infinite loop. And from the terminal, from the console, the way to get out of it is pressing Ctrl+C. And in Jupyter Notebook, that would be This is not a code cell. In Jupyter Notebook, the way would be pressing this stop button here. And I have just shown you that there is different types of cells here. You can add a cell from this plus button, and there are several modes in the cells. One mode would be that a cell contains some code. The other, Markdown, it will be just about putting some text comments between the cells. You can change the type of the cell by clicking on this drop-down menu. And Markdown is the syntax that is used in Jupyter Notebooks. So there are nice fancy styling you could do within the text. So if you double click on this, there are some examples of how to italicize some of the characters there, boldify there between double underscores, and put that in code mode by putting some part of the text inside the pair of back quotes. And you can even use formulas. Those are tag formatted. It goes between the double dollar signs. And the syntax here is for representing some formula widely used in any mathematical documentations. Theta equals fraction of L to the n divided by KT to the L to the n. And that formula looks like this when rendered by pressing Shift Enter on them. And there are nice shortcuts you can use. Shift Enter to run the current cell. B, outside the code editing mode. By the way, you can exit the code editing mode by pressing Escape button, Escape key. And from outside, you could press letter B to add a cell below the current cell, A to add a cell above the current cell, Y to change the cell to code mode. So if you press Y on this thing, it goes to the code mode. And if you press M, then it will go to the markdown mode and become the text cell again. And there are more shortcuts you can explore around. And they can be converted to other formats, such as HTML, LaTeX, Markdown, Python code, and many others. In Jupyter Lab, there's File and Export Notebook As. And you can see various file formats you could try to use. Executable script will give you .py file. And for homework, you will be asked to submit two files. One, this notebook file, .ipymb, and two, .html file. And about saving your notebook, actually, regularly Jupyter Notebook saves itself automatically. And if you want to force save yourself, there is a save button, keyboard shortcut, Control S on Windows or Command S on Mac. And if you are on Binder, your workspace will be destroyed after the virtual machine turns off. If you want to keep the notebook you edited, you need to download your notebook on your local machine. File, download as. Notebook. Do I see that here? Oh no, just download, I think then. And this will give you that IPYMB file downloaded. And how to properly close your notebook. Just closing this window does not close running the kernel. Does not close the running kernel. So if you just close this tab, the kernel is left open, still waiting for another code to run. And it may take up some memory if not closed properly. So if you are running on shared computer, you should be mindful of that part. On the dashboard, you can see the green dot indicating that the kernel is still running. And here you can see which kernels are running back there. Yeah, I have lots of unclosed kernels there for other classes. But if you want to make sure that the kernel is closed, you have to press X button for each of those notebooks. There also is File, Close and Shut Down Notebook button to make sure that your notebook is closed. And when you reopen the notebook, the output will still be there, but kernel would be wiped out. So no cells executed so far, no variables available to you. And one way to run the code again would be the thing I told you earlier, kernel, restart kernel, and run all cells. And there are nice example notebooks available on the course webpage, as well as some blog posts. And we will review some important libraries in machine learning in the second hour. For now, let's look at some of the nice examples of Jupyter notebooks. Some bioinformatics information application is here. And some nice visualization that gained popularity across stream learning. It's called TSNE. So you can see that kind of visualization here as well. And there are many examples in applications in genomics, cell and molecular biology, ecology, data visualization, generic data analysis, etc. For now, let's go to the break and let's return at 10:05. So before the break, we talked about the Jupyter Notebook application and basic concept of about what machine learning is. Let's talk about some important library that will be used when we do machine learning in Python. Python core is something very lightweight and includes nothing much useful in terms of scientific computing. It doesn't even have numeric arrays. And what makes Python possible to do lots of machine learning and scientific computing these days is through installation of external libraries. And as I mentioned earlier, Anaconda distribution of Python that ships with many of those packages for scientific computing. So libraries has become important characteristic of how Python works, and each separate application has its corresponding libraries. And the first of that would be NumPy. a package working with numerical arrays. Numbers stored in memory right next to each other in regular pattern. Python lists can't even do that. SciPy, scientific Python. It is user-friendly, efficient numerical routines that would include numerical integration, interpolation, optimization, linear algebra, and statistics. We will not use that package that much in this workshop. And then we have a package called matplotlib. Nice package for plotting things, borrowing syntaxes from MATLAB back then. Back then, MATLAB was one of the most popular when matplotlib was created. And we have pandas, package for data analytics. This one borrows syntaxes from R's data frames, short for panel data analysis. It is important package in data analytics in general, but we are not using that much of that in this workshop as well. The key package to be used in this workshop is Scikit-Learn. That is a lightweight package for machine learning. And the ecosystem, including all these packages, is called NumPy or SciPy ecosystem. They all build on top of the NumPy package for numerical arrays. So for this hour, we'll explore two key libraries used not only to machine learning, but also to any quantitative project written in Python. NumPy is optimized for vector calculations and matrix operations. Matplotlib is a package for you to create virtually any visualization. 2D plots, scatter plots, bar plots, etc. Let's go to NumPy. In standard Python, the data collections are in the list. And what do those lists do? There are several nice things of the list. Lists can contain any type of values. It can contain different type of objects. And it supports easy insertion of value, easy deletion, easy concatenation of different lists. However, for scientists, the list poses heavy limitations. Notation-wise, sum of two lists is concatenation, not vector addition. And lists are slow when the lists are large because list is designed to be flexible for it to have any different types of objects. But in many cases, in scientific applications, we just have numbers. And we need something optimized for those numbers. And there are limited functions available in NumPy, in lists as well. There are no functions for taking means or variances directly. So scientists would like an object that is closer to the notion of vector or matrix, collection of numbers, put right next to, with the numeric data put right next to each other in memory. In Python, a list of numbers that refers to Well, when you do that, they are just collection of references to those numbers data somewhere in memory. So that cannot be efficient enough for this kind of applications when working with numbers. And NumPy is what implements that kind of numeric arrays. So virtually all other scientific libraries in Python are based on NumPy these days, and they are dubbed NumPy ecosystem. So NumPy is an array for large multi-dimensional arrays and matrices and mathematical operations with them. To use NumPy in your code, what to do is simply importing the package first. So we say import NumPy in our code. And to create those numeric arrays, the syntax looks like this. There is a function called array inside the module called NumPy. So we call that function by using the syntax numpy.array, and in the parentheses, we put something that could be converted into an array. A simple example would be a list. It could be something else defined in other packages that could be turned into lists. And that could be turned into numeric arrays. So we compare a list with several numbers, and that turned into NumPy array. A list with numbers 1, 2, 3, 4, 5. And if we print type of A, that is a list. And if we pass that to the function numpy.array, then we will get numpy and the array for its type. N-dimensional array is what ND array is short for. We're going to use NumPy a lot, and 5 letters seems to be too much to type each time. So it is extremely common to rename it as NP. NP will be just a short nickname for NumPy, and this is kind of idiom in Python, which over 99% of people using NumPy will use. Import NumPy as NP. Then this function can be called with np.array now. And this is basically creating a new NumPy array with a different list 5, 4, 3, 3, 2, 1. Then let's compare some mathematical operations. We would think list plus list and list plus NumPy array. Let's compare that. Sum of two lists, 1, 2, 3, 4, 5. That is just repetition of the list because it is concatenating two lists together. But if you do that with NumPy arrays, what we get is another NumPy array adding the values between the two arrays. So we get 6, 6, 6, 6, 6. When the original array is 1, 2, 3, 4, 5, and C was 5, 4, 3, 2, 1. And NumPy provides vectorized and element-wise operations in many cases. You can add a constant to a NumPy array. So you add the same number to each element in that array. This will give you 7.1 plus 1, 2, 3, 4, 5. So 8.1, 9.1, up to 12.1. You can also multiply by a constant. That will be multiplying each element in that array by the same constant. So we get 2.5, 5, 7.5, 10, and 12.5. Exponentiation goes element-wise again. 1 to the 3, 2 to the 3, 3 to the 3, 4 to the 3, and 5 to the 3. And you could also do operation between two different arrays, and those operations will be element-wise. Element-wise product, division, and modulo operations are all available. So this will be 1 times 5, 2 times 4, 3 times 3, 4 times 2, and 5 times 1 to get 5, 8, 9, 8, 5. And we could do element-wise division this way. 1 over 5, 2 over 4, 3 over 3, 4 over 2, 5 over 1. And element-wise modulo as well. 1 modulo 5, 2 modulo 4, that is 4. 3 modulo 3 is 0. 4 modulo 2, that is also 0. 5 modulo 1. Anything modulo 1 is 0 anyway. And many numeric functions are also defined, and they are also element-wise. Exponentiation, sines and cosines. Let's talk about selecting elements and sets of elements from your NumPy array. And those basic indexing is same as in lists. But keep in mind that Python uses zero-based indexing, unlike one-based indexing that is used in many other languages, R, MATLAB, Fortran, or Julia. Python is in the family of more general purpose programming language, so it uses zero-based indexing, which is widely used in those kind of languages, including C, C++, Java, etc. Zero-based indexing means that the first item in the collection is indexed with number 0, and that might introduce some confusion. In this workshop, I will say terms first, second, third to mean one-based indexing, and index number 0, 1, 2. They would all mean zero-based indexing. So the first element in B, the NumPy array with elements 1, 2, 3, 4, 5, that will give you the number 1, which was the first element in this array B. And index 1 to array B will give you the number 2. That was the second element in B. To get the last element in B, we can use the index -1 to get the number 5. And to select all the elements in B, we can index by colon to get everything. And it would be a copy of the array B, technically. And we could do slicing, starting index to ending index. But remember, the ending index is not included in the result. So this will give you elements 1, 2, and 3. Elements with index 1, 2, and 3. And those values will be 2, 3, 4. And for slicing, we could put a third number in these colon notations: starting index, ending index, and step size. So this notation, B 0 colon -1 colon 2, will give you index 0 to the last index in steps of 2, except for the last one. That would be numbers 1 and 3. Start, end, step size, and some of them could be omitted. And if they are omitted, that will mean some natural starting point or end point of the sequence. So this will mean indexing from 0 to end in steps of 2. That will give you 1, 3, and 5. And there's a quick way to get a reverse of this array B by putting colon, colon, -1. If the step size is -1, then starting point will be considered to the end of the sequence, and ending point will be considered the start of the sequence if not put in by default. So this is a quick way to reverse a sequence. That was basics indexing and slicing to remember. And let's take a quick look at the Python syntax in object-oriented programming. In this workshop, we do not assume much knowledge in object-oriented programming, but those packages are built with those concepts, so you will need to know how to use them at the very least. You don't need to know how to write them, but you better know how to read them. And Python objects have attributes and methods. Attributes will be the properties like shape, length, number of dimensions, etc. The property that belongs to an object. And in this case, a NumPy n-dimensional array. And methods are actions or functions that could be applied to or performed on the object in question. Summations or product of all the elements are examples of that, and that can be used by the syntax. The variable with the array dot method name, and then we pass some arguments to them. For simple attributes, the syntax is array name dot the name of the attribute. So beta size, that is a simple attribute. Number of elements in the array is what you get, 5. And dim, number of dimensions in the array, and what we put here is simple one-dimensional array, so we get 1. For two-dimensional array, you will get 2, and that will be treated as matrices, and you could have higher dimensional arrays. But in most cases, in this workshop, you will see one-dimensional array or two-dimensional arrays. One-dimensional array, vectors, two-dimensional array, matrices. Shape will give you a tuple for size of each dimension. And B is one-dimensional array with length 5. So that will give you a tuple of length 1 containing value 5. And sum is a method on the array B. If you run this, we will get the sum of all the elements in that array, giving you 15. 1, 2, 3, 4, 5. Python has a built-in function for that, but that is designed to work for any type of numbers. Any type of data which you can apply the summation operation on. And to do so, this is slow. To get the product of all the elements, we have that prod method here. 1 times 2 times 3 times 4 times 5, which is 120. And we can actually see the list of attributes and methods for n-dimensional arrays from this link. This is official NumPy documentation of the most recent version of it, 2.2. And it tells you how to create an ND array. The attributes available, such as transpose, data, view part, imaginary part, number of bytes, number of dimensions, shapes, base type, etc. And you also see the list of methods available. All, any, argmin, argmax, comsum, cumulative sum, comprod, cumulative product, flatten, max, mean, min. Variable is what we will talk about later on in this workshop. We have sum here, etc. So if you need that thing, first place to visit would be here to see what is available. There are other ways to create an array. Like Python's range, we have a range that gives you the range in the form of array. The difference from the range function would be that the arguments can be floating point numbers. So you could do something like this. Starting at 1, stopping at 5 with an increment of 0.5 to get the list, to get the array of 1, 1.5 up to 4.5, 5 not included. There also is the function linspace. The values from the starting point to the end point with the number of subdivisions. Then they will be spaced linearly, same distance between adjacent numbers. So if you do linspace 0, 10, 4, then you will get numbers 0 to 10 linearly spaced, same distance between elements. What we get in this case would be 0, 3.333, 6.6667, and 10. 4 elements starting with 0, ending with 10, and same distance between each element. Notable difference from a range, this includes the endpoint. And you could also do linspace 287, starting with 2, ending with 8, linearly spaced, with 7 elements, and that, in that case, the spacing will be at 1 between each other. So you could cast that to integer and have an integer array as well. And casting elements to integer, that is done by this method as type. So with this, we are casting an array with floating point numbers to integers. Did we talk about dtype? No, I don't think so. So if you do a.d type, that is one of the attributes of NumPy array. Oh, what would that be? D type. Data type of array's elements. Oh, A was a list. B was the array. We get the data type inside for each of the elements in that array. Int 64 means 64-bit integers. Often that is the default integers in many programming languages. And we use that in NumPy. And D type of this thing each element takes up 64 bits in memory, so which is same as 8 bytes. If you do list space like this, the D type will be float 64, 64-bit floating point numbers. And often that is called double precision numbers when you learn compiled language often. And that can be changed to other types by casting like this. And that will give you integer now. By the way, there is a tab key you can use for auto completion in Jupyter Lab. So, which is nice for you. And if you can get Google Copilot available, then auto completion comes much quicker, I think. Function. There are also functions to create a new arrays with filled with certain values if they are ones and zeros. And that ones will give you an array filled with ones with that size, and that zeros will give you an array filled with zeros with that size. In this case, it is 5. And it will be floating point numbers. So far, we've only shown the code with one-dimensional arrays. Let's move on to higher dimensional arrays. How about 2? Two-dimensional arrays. To represent that kind of thing in lists, that would be nested list of lists. A list with 3 lists, each list representing each row. And you can turn that into a NumPy array to get an array of size 3 by 4. This is a 3 by 4 matrix. And each inner list representing each row, as you can see. Shape of this array, 3 rows, 4 columns. Number of dimension would be 2. If you print out the size of it, that will be 12. That is the number of elements in this array. And keep in mind that this only works if each inner list has the same length. That is important. for a multi-dimensional array to be defined.
Data is not the same then.
What if
Data is not the same then.
not the same data type, or what do you mean by same data?
That's three data points. The other is 4.
So if you do something like this, is that what you mean? It will fail. That's not possible. Each row should have the same number, the same number of columns for NumPy array. For n-dimensional array, you need that the size to be regular in the form of rectangular shape. That is the requirement for an n-dimensional array. And if you have some missing value and you want that to be filled in, one way will be something like this. Filling in with not a number value. Then this will define a proper n-dimensional array. 3 by 5. 3 rows, 5 columns. But by having not a number there like that, not that many mathematical operations will work properly. So you will want to impute those values or remove those values when in general data analytics scenarios. And this is 2 dimensions, and you could go higher dimension. How about 3 by 2 by 2? By splitting these dimensional 4 into 2 by 2 subarray. Then that will give you this 1, 2, 3, 4, 10, 20, 30, 40, 100, 200, 300, 400, each of them being 2 by 2 array. And we will have array of those 2 by 2 arrays to have shape of 3 by 2 by 2. Then you can index this kind of array dimension by dimension. So you could do B0, colon to retrieve the first subarray here, 1, 2, 3, 4. And you could do similar to the second dimension, B colon 0 colon. That will give you this 1, 2, 10, 20, 100, 200. 1, 2, 10, 20, 100, 200. The second index is representing the row index of each submatrix, basically. And array with 1 dimension and 10 elements is different from array with 2 dimension, 10 elements with size 10 by 1. And that can be reshaped between each other using the function, using the method reshape. So let's start with 1 dimensional array of length 10 like this. And then let's reshape it to 10 by 1. Then it is a matrix with 10 rows and 1 column. Shape will be length 2 tuple now, 10 by 1, and dim 2. And why I'm showing this today? Because this is a common issue you will deal with later on this workshop. Because some of the functions require two-dimensional array as an input, some of them 1D. And often we just need one column array. And this kind of reshaping will be needed in those cases. And indexing works the same to access element in position I, j. We are just working with two indexes separated by comma inside that square brackets. Array I, j with access position I, j. And you can select entire column or row by using colon. And you can also use slicing for some subset of those rows or columns. So with this array, the element at position 1, 2, what is that? Could you tell me what number this would be? Anybody? Yeah. So sorry. So could you tell me what this would be? A1, 2? $30? Anybody else? $30? It is 30. Row index 1 is this, refers to this row, and column index with 2 refers to this column. So that would be 30. Indexing this way, A1, 2. That is also possible. That will also give you 30. But just like how nested list is indexed. So that is also possible, but it is less efficient because it takes two steps. A1 is computed first, and that creates a copy of the row index 1 of A. And then it accesses index 2 of that vector. And doing A1, 2 directly accesses the value at that position without copying the row. So row number 2 of array A can be done this way to get 100, 200, 300, 400. Column number 1 of matrix A could be received this way: A indexed by column, colon, 1 to get 2, 20, 200. Then how would you reverse the order of columns in matrix A? We talked about reversing the order of the elements in a sequence earlier today, and we are exactly doing that. We are selecting all rows without changing, and for the columns, we reverse it. And the indexing is column, -1. Good. Then that will give you the order of columns reversed. Now let's try to access elements by logical tests. Let's recall how to perform logical tests in Python, where the result of that would be Boolean values, true or false. Oh, sorry. Values in array A looks like this. And you could put inequalities to check if an array is greater than some value or not. And that can be done element-wise by putting inequality sign to an array. A greater than 25, then we'll check if each element is greater than 25 or not. So what is unique with NumPy is that we can select elements based on the result of this logical test. You can index an array by a Boolean array. So this is a valid NumPy syntax, giving you all the elements greater than 25, 30, 40, 100, 200, 300, and 400. What is more is that you can assign values to it. You could do something like this, so that each of these values are replaced by 25. One, two, three, 4, 10, 20, 25, 25, 25, 25, repeated. So you can clip the maximum value at 25. Then here's another exercise. How would you replace all the odd numbers in ARR with -1? And after that, how would you replace all the even numbers with -2? Let's do it over the break, and we will return 11 a.m. So how would you solve this question? We're replacing all the odd numbers in ARR with -1, and the elements with odd numbers would be checked by this modulo operation, ARR modulo 2. If that is 1, then they are the odd numbers. Otherwise, that is even numbers. And we can assign values to it. So we could put -1 here. Oh, I didn't run this one. Then we would get all the odd numbers replaced by -1. And how about replacing all the even numbers with -2? That would be ARR modulo 2 equals 0 equals -2. That will give you all the elements, all the even numbers in that array to -2. Now let's talk about some visualization. Matplotlib. Scientists draw graphs all the time, and with the power of Matplotlib, one can even do this kind of video. This is 400 megabyte video, so I didn't put it on the GitHub repository. But yeah, you can see as time moves on, you can see the color changing a bit. And the graph for concentration of calcium ion over time, you can see it, and the level of fluorescence as well. And this would be just plotting the data on the XY plane. Similar thing here. And this would be location-wise fluorescence intensity for each of those pixels. And for each second, we have the value of the current value. We have current value of fluorescence, the calibrated concentration of calcium ion, and the fluorescence map. And that can be turned into an animation in Matplotlib. But we are not going that deep for this workshop, and we will remain with plotting things. And often we will use the pyplot subpackage of Matplotlib. Basic usage: plt.plot y to plot an array, and plt.show to display the figure when plt is the nickname given to the pyplot subpackage of matplotlib. So this kind of nickname is very common for matplotlib. Let's put 1D array first, an array with 0, 10, 3, 4, 2, and we plot y. Let's see what we get. It is a graph basically. The values in that array 0, 10, 3, 4, 2 versus the indexes 0, 1, 2, 3, 4. Let's do something more complicated because matplotlib can do much more. In a few lines, we can have a really nice results. How about plotting sinusoidal curves? X will be values in a range, and y1 will be sine x, a sine of half x, and y2 will be sine of half y, a cosine of half y. If we plot that, the argument now is x and y1, x and y2. We are plotting y1 versus x and y2 versus x in that case. Then we get two curves drawn in the same plot. One for the sine function, the other for the cosine function. And we can decorate this further. Plot function has nice keyword arguments to change the configurations. O hyphen hyphen. Change the markers to circular one, and it draws a dashed line instead of continuous lines like this. You could put marker size, width of the line. You could put a label, and you can set the color of the line to red like this. Similar thing happening on the second line. This time the markers are square, again dashed line. Marker size, line width, color K means black, and we label that with cosine. And we can also put X label and Y label. The label to put on the x-axis, this time with time, and the label you put on the y-axis. Let's just randomly call it fluorescence AU, because that is what we just saw earlier. And we could change the locations where these ticks are. That is done by y ticks. And that will give you -1. That will give you ticks on the y values of -1, -1/2, 0, 1/2, and 1. And we can also display the legend in the figure using the plt.legend. And the result is this. Circular markers, dashed line, label sign, square markers, dashed line, black, that is cosine. And we see X labels, time here, Y labels here. Ticks are now on the 5 points we have set to. And we also get the legend without frames. It is done by frame on equals false. If that were true, we would have gotten the square frames around a square frame around it. And this is a figure that will be kept within a Jupyter notebook. So you can share this notebook with this plot included by just sending around .ipymb files. But more often, you will want to export those files in the form of PNG or JP or JPEG or others, SVG for vector images as well. To do so, here's the usual structure. You would first define the figure with figure size. How about 5 by 3? Then we will plot things just like before. And at the end, we are adding dot tight layout function call, which will fit the figure we have to the frame to make sure that all the figures are captured within our figure boundary. And instead of plt.show, we run save fig with the file name fig1.png, and we are also putting dpi keyword argument. That means dots per inch. And then we close the figure to save the figure. The others are the same as before. If we just run this, we get a new file just created here, fig1.png, updated seconds ago. And then what would be 3 by 5, 3 inches by 5 inches image that we have just created. And some examples of those matplotlib. There is a nice gallery on their website, matplotlib.org. And there are many beautiful examples. Lines, bar chart, broken bars, cap style, curve with error band, filled polygon with some error bars. A lot of beautiful examples you can see. And if you click on each of them, you will see the code to create them. Color maps or heat maps. You can also see that kind of thing. Contour plots, which we will use later on. We'll talk more about it tomorrow. Now let's talk more about machine learning. What type of machine learnings are there? The most fundamental types would be supervised and unsupervised learning. Supervised learning, we consider the pairs of example inputs and their desired outputs or labels. For classification, those labels will be the category that each input belongs to. And the examples would be decision trees, k-nearest neighbor classifier, naive Bayes. And for regression, the desired output will be some continuous value, and we want a model to predict which continuous value each sample corresponds to. Unsupervised learning deals with data without labels, and the goal is learning the structure among them. One fundamental task is clustering, which is basically grouping our samples in predetermined number of groups in case of k-means clustering. The number of groups are not necessarily predetermined. And some of those examples include density-based clustering. There's a thing called dbScan over there. And there are several different types of learning as well. Semi-supervised learning. Some of the data are labeled, some of them are not in that case. Reinforcement learning, based on what is on the environment, finding the optimal action to take. In this workshop, we focus heavily on supervised learning. As I mentioned earlier, supervised learning requires examples or training data set from which the model will learn to reproduce the patterns. We will need training set, the label data set passed to the supervised learning to produce a model. It will learn the model so that given some input, it will predict some label. After learning the model, new observations will be provided to those models, and model will make prediction of the prediction for the desired output. It will create some prediction or classification in the case of classification cases. Classification is creating a model that identify each sample by their category. Sorry, identifying category based on their values inside it. Examples would be identifying cells by their shape. On the x-axis will be the feature. On the x-axis and y-axis will be the features corresponding to each samples. And visualize here our location of each sample on 2 dimensions and colors representing their desired classification result or their labels. And often the classification amounts to finding some boundary for the model to decide if the sample is in one class or another. And that boundary could be something like this, H1. If it is on the left side of this line, it will be class 1. On the right of this line, it will be class 2. Similarly, we could have this kind of model like this, still classifying those 2 classes. And this model, the model represented by this line, might not be considered very good, because on one side of the line, it has mixture of black and white dots, and on the right side of it, we have one white dot. And the goal would be finding the nice line, the boundary between the 2 classes. By seeing this one, which one would be the best boundary between the 2 classes? H1, H2, or H3? Maybe H2? H1 still classifies all the samples correctly, but H2 has farther distance from the samples, right? We will talk about that kind of stuff later in this workshop. Regression would be predicting the target variable value based on some of the input features. For example, examples would be creating a function that estimates the cell volume based on the shape of the cell, length and width, etc. Linear regression will be represented by a line, but there could be more complex models. Let's talk more about classification. Identifying the category each input belongs to. Often, the categories are predetermined. Identifying the type of fruit based on width and height, lemon versus orange. Identifying the type of cancer cell based on its shape, if the cell is benign or malignant, for example. The target would be the category we want to identify, and to do so, we will look into features, which are individual measurable properties of objects studied. could be width of the cell, height of the cell, smoothness of the cell, factor dimension of the cell, etc. The procedure, the model first learns from the example on how to discriminate between different classes. And when the model is trained, that model is used to make some predictions. And for regression, it estimates the value of the continuous variable, estimating cell volume given length, height, and smoothness of the cell dimensions. The target would be the desired continuous variable, for example, volume. Do you have questions so far? So we have classification and regression. And let's think about regression scenario where we are predicting continuous value. And let's say we are trying to perform a regression using these data. On the x-axis is the feature, and we will use the values on the x-axis to predict the values on the y-axis, the target. And which model would you use? For this kind of thing, it is natural to use some kind of curve to represent a model, right? And ideally, we would want something like this, going through the data points smoothly, it looks like. But what if we fit a linear regression on this data? The set of models would be too rigid. We are constrained to be a line with this, so we would never get this kind of curve. So the model we get looks like this. Model is constrained to be too simple. So the model does not take full advantage of the data. We cannot catch those details smoothly going down and then up again. Something is missing. This kind of situation is called underfitting. However, that is on one end. On the other end, what we have would be complex model. Actually, if we want to go through this data point, we could just twist and turn our curve so that it goes through all the points you can see here. However, then that will make the model too complex, looking like this, for example. This is 20-degree polynomial fitting the data. And it looks a bit too wriggly. This model might be too complicated or complex than the data requires. But this still is a model. The question will be, how would these model generalize? What we are interested in is putting the new observation to the model and get the prediction. So what we want from our model is to perform well when the model not seen by the when the data not seen by the model is provided to the model. That is why we try to generalize the results. That is to avoid underfitting and overfitting. Say some new data are collected. The overfitted model describes the training data perfectly, but it fails with the new data, those red dots. It goes off pretty much. And if we had this kind of model, it would have fit nicely. The question would be, how will we determine if this model is underfitting or overfitting? When we are underfitting, that is when a model cannot adequately capture the underlying structure of the data. What we would do in that case is choosing another model with higher complexity. When we are overfitting, the natural thing to do is to do some model selection and cross-validation to make sure that model generalizes well and simplify model a little bit to avoid that kind of overfitting. Because overfitting is when a model reproduces nearly perfectly a particular set of data and likely fails to explain new data points or predict future observations. And determining if the model overfits or underfits, that step is called model validation. So this is a typical machine learning pipeline. With the collected data, first we will select the feature to be used on our model. Because some features are not really informative, especially on high-dimensional genomic data, we will often have millions of features to fit sometimes only 100 samples. And most of features will not be informative in that case. So in that case, feature selection is important. Then we will build our model construction based on the features we selected. And if it is not working well, we would go back to feature selection. And to check if the model is working well or not, you would do model validation. To check if the model is overfit or underfit. And in this workshop, we will concentrate on model construction and model validation. We will go over several different models for classification. Then we will learn how to tune those models by changing some of the hyperparameters. That could be depth of the tree. That could be some parameter changing the complexity of the model. One example would be decision tree. Classification is represented by a simple flowchart style structure. And learning rule is very simple. Each node of the tree represents where we make a decision based on one of the features we have. It selects a feature, and it will have a threshold that separates data point from two different classes, the best. So learning rule is selecting a feature and selecting a threshold. And that is repeated until we have a satisfactory model. There is some stopping criteria to determine if the learning is finished or not. At the end of it, we would have this kind of tree structured model. The learning rule might first select width for a feature that best separating two classes. And then it might have determined that the width value of 6.5 best separates between the classes. And then we have only one feature left, height. If the width is greater than 6.5, we check height if that is greater than 9.5 or not. If it is greater than 9.5, it will classify our samples to be lemons. Otherwise, it will classify our samples to be oranges. On the other hand, if the width is less than or equal to 6.5 centimeters, we could check if the height is higher or lower than 6 centimeters. That is another threshold chosen. If higher, then it will be considered lemon. If lower, those will be considered oranges. There are some terminology we use for decision trees. Root will be the node on the top of the tree, the first overall splitting, the very first feature, and the very first threshold determined. Leaf nodes, they are the nodes at the bottom of this tree, where we make the final decisions on whether these points are lemons or oranges. No more splitting happening. And depth of the tree would be the furthest distance between the root and the leaf nodes. So this will be the tree of depth 2. Because we had 2 layers of decisions. Then we could think about what will control the complexity of the model. The quickest thing you can think of would be the depth of the tree. If we let the trees to be deeper, the models will be more complex. If we let the depth of the tree to be small, the model will be simple. Yep.
Seems like we could just, so we have a depth of 2, but we could just have a depth of 1, though, right? Where we just have,
With only that one.
if the height is above 9%, that's
Uh-huh.
really, we can make one, 2, 1. So the fact that we have a higher depth,
Yeah.
is that actually having greater utility as opposed to 300?
So if you have higher depth, then it will have higher flexibility, and it will be able to classify. It will have many more options to make classifications. The limiting the depth will be controlling that kind of complexity in the model. With higher depth, it will be more flexible, and with the training data, it will gain higher accuracy in general. Otherwise, if we just have the node on the top and with greater than 6.5, if we only have that, and one side, and then one side would be called oranges. Oranges. lemons. If we just had this, what do you think? The model is simpler than this one, but the accuracy would be lower.
But if we were to have the height greater than 95, that would still be able to discriminate the runs in the point, right?
That is the first step the learning will take. So with this data, the assumption here is that the first thing it chooses would be width. Width that separates the two classes. That is the first thing the learning procedure will do in this case. So we will not get that model having height on the top. Does it make sense to you? It depends on data and the algorithm. And in this illustration, I would assume that width is the feature separating the two classes. So it is chosen first. But yeah, algorithm might do the wrong thing and might have chosen height first. That depends. But yeah, that will depends on what is on the training data and the samples the algorithm sees and mathematical model the algorithm utilizes. Does it make sense to you?
Yeah.
So for the remainder of today, let's talk about how to build this kind of model using Python, using a package called Scikit-Learn. And we will use, and there are some data sets that comes along with the data, comes along with the package. And in there, we have some breast cancer Wisconsin data set. Scikit-Learn, the name of the package we use in Python is sklearn. And we are importing matplotlib.pyplot as PLT as well. And Scikit-Learn has a sub-package called datasets. And there is a function called load breast cancer that will load the data. This will be some dictionary lookalike data set. We have data points in a NumPy array, and we have target and some descriptions on what the data is about. Target label 0 means malignant, and label 1 means benign. The target name says, and this is more description of this data set. And what the features are is also listed in here. Feature names, mean radius, mean texture, mean perimeter, mean area, mean smoothness, etc. We have 30 of them. Type of cancer is called bunch here, but you can just understand this as some specialized case of a dictionary. And you can access the data using bcancer.data. And that is a NumPy array. And let's see what is in this. The shape of this NumPy array data is 569 by 30, and shape of this array, the target, is of length 569 values. So we have 569 samples and 30 features to work with. Features are the set of quantitative characteristics about each of your samples, and we have 30 of them, about the shape of the cells. And target is our objective, the labels 0 or 1, malignant or benign. During the training, the target is known, and they are called ground truth. So if we print the target values, 0s or 1s, it will look like this. And let's inspect just one of those samples, the very first one with index 0. And that one has value of 0. So that cell is malignant. And it has these features. By accessing a sample using only one index, that gives you a single row of a matrix containing 30 values. You could have done the same thing with this as well. And the value of target 0 would be 0. The features are measured based on microscopic image of the nuclei of the cells extracted from the patients. Radius, texture, parameter, area, smoothness, compactness, concavity, concave points, symmetry, and fractal dimension. And those names are available in the feature names attribute. We have mean of them, we have error estimate of them, and we have worst case values of them for each of those 10 values. So we have 30 features in total. Our goal is to create a model that receives numbers like these and predict whether they are from a malignant or benign cancer cells. And that model can be loaded from the Scikit-Learn package for decision tree classifiers. That is inside the tree subpackage of Scikit-Learn under the name decision tree classifier. This is the name of a class, including some of the attributes and methods, just like NumPy and the arrays. And you can check its documentation from this documentation page for Scikit-Learn. It gives you some information needed to create those classifiers. And there are attributes and methods you can check. For now, let's limit the depth of the tree to be 4. And we are creating a decision tree classifier with max depth of 4, and we are assigning that to a variable. And we can do several things on the variable, and often with Scikit-Learn model, what we want to do is fitting the model, learning the model. And that would be done by passing the data at hand as arguments. The first argument will be the features, 2-dimensional NumPy array, number of samples by number of features. And the second argument would be the labels, 1-dimensional NumPy array, 0s or 1s in this case. After running this, we get a decision tree classifier model.
Sorry, we have like so many features. Is that like inputting all the features?
Yeah, we are inputting all the features now, 30 of them.
So what is the depth here means?
Depth here means the limit of the depth on the decision tree. For this one, we have depth of 2, right? And by putting 4 there, that means we are training a decision tree, but the depth of that tree will be limited to 4. We are not going any deeper, even though doing that will make our model classify the training data better.
So you're still considering all the features.
It is still considering all the features. It will be considering all the features, but each splitting point will select one of those features. And for each split, the learning algorithm determines which feature separates the samples the best. Among all the features being considered. We know that sample 0 is a malignant tumor, so we want the output from the model to be 0 when we put the data for row number 0 in that data set. How do we check that? We have a predict method. Beacon model that predict. We pass the row number 0 of our data. But the predict requires the data to be two-dimensional array. So we are wrapping that around. So we are wrapping that with square bracket. And we get a 1D array with a 0. So it is predicting our sample correctly. How about sample 19? This is a benign tumor. How would you check if this sample is classified correctly or not by our model? Then we'll be printing because their model the predict. And we would be passing row index 19 to this model. And make sure to convert that to a two-dimensional array. I forgot to close this parenthesis. And it gets 1, so it is correct classification. So given this data, the model predicts the sample to be a benign cell. We can also evaluate the prediction of the model on the entire data set by just passing, because there's that data there for the predict method. Then we get a vector of 569 numbers. Let's compare that to the ground truth. The result will be the ground one-dimensional array of Boolean values, truths and falses. How would you do it? Let's assign that to a variable called prediction correctness. We got BK predictions as the true false labels predicted by our model. And we know the ground truth is, and that is inside bcancer dot target. And just putting double equality sign between them, that will give you a Boolean vector, length of 569. Truths or falses. And and with our model, it was able to predict a lot of them correctly. How many of them are they? Every true means that prediction that matched its corresponding ground truth, and false means our model failed to predict the correct label, known as misclassifications. And let's visualize how many correct classifications and how many misclassifications we had with this classifier, with some histogram. Let's just turn this prediction correctness variable to integers. And hist is for building a histogram. And let's put 3 bins there. And let's set the label to be count. And let's put x6 this way, so that the bins of so that the histogram with 3 bins represents correct classifications and misclassifications. The value of 0 means misclassifications, and value of 1, that is where true values are transformed into. So those are correctly classified samples. And we have much more correctly classified ones than misclassified ones. Actually, we can count that using this method, prediction correctness dot sum, because sum gets the summation of all the elements, and trues are ones and falses are zeros. And we can say that we have 559 samples correctly classified by our model out of 569. Then what is the misclassification rate? 10 divided by 569, right? And how do we get those numbers using our code? This number divided by, the number of total samples number of total samples. How do we access that? That is the number of total samples minus the number of correctly classified samples divided by number of total samples. And we could have done this in many different ways, of course. Misclassification rate 1.7%, 75%. More than 95% of the data were classified correctly. But we have to think about this. Are we confident in this result? How can you tell we are not overfitting? If the classification accuracy will be close to 98% when we pass the data unseen to the model yet. We don't know that part. We are just checking that the classification accuracy on the data points that our model learned on. And how to measure that, how our model generalizes well, telling whether if our model is underfitting or overfitting. That will be discussed in tomorrow's workshop. So tomorrow will be the more important topic. So hope to see you then. We'll also talk about more classification models and how to validate them, making sure that we indeed have prediction power and generalization. Thanks for coming and hope to see you tomorrow. Any questions? Yep. Other questions? About your group?
How does this function work?
Oh, what the physical tree means. Okay, let's talk about that. So we are creating a histogram. And histograms are represented as some graph with vertical boxes, right? And that is the count of the values inside given intervals. And number of bins means number of those intervals we are defining. And we are putting that intentionally to 3, knowing that we have values only on 0 and 1. So we have some empty space here.
Oh. Thank you.
Thank you.
So it's 3 bins, just like 0 to 0.3.